Hello everybody, and welcome back to another geometry lesson. Today, we are going to take a look at section 9.6, which is all about solving right triangles. Now, we'll talk more about what it means to solve a right triangle in a bit, but just know that this is going to require us to be able to find different sides and find different angles. Now, we know that when we were using our trigonometric ratios from last time, we could use those to find sides. You start with an angle, such as, let's say, 32 degrees. You have a side, and you have another side, and you can use a trig ratio to solve this. The sine of 32 will equal 3 over x, for instance, because sine is opposite over hypotenuse. The opposite from this angle is 3, the hypotenuse is x. But what if I gave you a different problem? What if I told you that this side here is 3, this side here is 5, and I wanted you to find this angle? Well, now we're sort of stumped. We know the sine of this angle is supposed to be 3 over 5, but that doesn't actually help us find the angle. It just tells us the ratio of the sides. Well, with every mathematical process, we like to have an inverse, or an opposite process. Start, for instance, with x equals 7. If you wanted to make the right side bigger, you could multiply both sides by 2 to get 2x equals 14. But we should also be able to reverse that process. So what's the reverse of multiplication? Well, that'd be division. And we know that if we divide both sides by 2, we end up right back where we started with x equals 7. It works for everything that we've done so far with numbers. Almost all processes have been reversible. If x squared equals 64, you could square root both sides to get x equals positive or negative 8. You could then square both sides again to end up right back where you started. Our goal today is to talk about an inverse, or a reversal, of our ratios. Right now, our ratios say, if you have an angle, you can find a side. We're going to reverse it to say, if you know your sides, you can find an angle. So let's take a look at these inverse trigonometric ratios. The inverses work like this. Let's say we have a triangle here, like so. And I'm going to call this triangle A, B, C. Now, it might seem confusing, but I am going to label the side that's across from angle A as side A, the side that's across from angle B as side B, and the side across from angle C as side C. This might not make a ton of sense right now, but trust me, it'll be super beneficial in the next lesson if we do this notation. Normally, we know that if we wanted to find the tangent of A, for instance, well, the tangent of A is equal to our opposite over adjacent, A over B. If the tangent of A equals A over B, then the inverse tangent is the process we can do to reverse it. And the formula goes like this. The inverse tangent of A over B will equal angle A. This symbol here, the tangent with the negative first power, is the symbol we use for an inverse tangent. Notice what we did here. We literally took the angle and the ratio of our sides and just had them swap places. Instead of the tangent of an angle equals a side, we have the inverse tangent of the sides equals an angle. That is how we can get our inverses. And of course, there are others too. For instance, if the sine of angle B was, let's take a look. The sine of angle B is opposite over hypotenuse, so that'll be B over C. Then the inverse sine to the negative first power, of B over C will give us angle B back. If you take the inverse sine of whatever number B divided by C is, you'll get the angle out of it. And finally, let's go back to our A notation. If the cosine of A is supposed to be adjacent over hypotenuse, B over C, then the inverse cosine, you guessed it, would just reverse the angle and the ratio of the sides. Like so. This is all an inverse is. It's swapping the angle with the ratio of the sides. So in exercise 1, for instance, it says, let's pretend that A, B, and C are, well, technically one of these angles isn't acute, so I'm just going to say are angles. Calculate the measures of each degree to the nearest tenth of a degree. Anytime we use an inverse, we're going to get an angle out of it, so the measurement will be in degrees. Right now, we have the tangent of some mystery angle A equals 3/4. But we know from our formula that if we wanted to take the inverse of it, inverse means to swap the angle with the ratio of the sides. We could say that the inverse tangent of, well, the side ratio is 3/4, that will equal angle A. To find an inverse tangent, you go to our trusty calculator. In our calculator, the inverse tangent button is in blue right above the tangent button. So to access it, we're going to need to press second and tan. Now we can put in 3/4. Oops, sorry y'all, realized you couldn't see my screen. And just like how the tangent of some angle is a number, the inverse tangent of some ratio is also going to give us a number. This time it's going to give us the degrees of the angle. So according to this, angle A is approximately 36.9 degrees. Nice! We can do the same thing with the inverse cosine and the inverse sine. If the cosine of B is 0.87, well then the inverse cosine of 0.87 will give us B. Similarly, if we wanted to see that the sine of C is 1, the inverse sine of 1 should equal C. When we calculate both of these out in our calculators, we are again using the inverse buttons right above the cosine and sine buttons. So the inverse cosine of 0.87 is 29.5, so B will be about 29.5 degrees. If we take the inverse sine of 1, we'll actually get exactly 90 degrees. So that is how we use inverse trigonometry. I want to elaborate on why this works. So, remember how before we started with an equation, we did something to it, and then we did the opposite to it? Let's see if we can do something like that. Let's say I give you the equation that we did in part A. The tangent of A equals 3/4. If I wanted to undo a tangent, we could apply an inverse tangent to both sides. And you don't need to do this whole process for every problem you do. Like, we skipped it for the ones we did together. I'm just showing you why it works. Just like how you can multiply both sides, or divide both sides, or square root both sides, or square both sides, you can also take the inverse tangent of both sides. Because the tangent and inverse tangent are opposites, these two will cancel out, leaving a by itself. We have a equals the inverse tangent of 3/4, which is what we got down here anyways. Cool. Exercise 2 is a bit different in that we're not really going to be using the inverse ratios to solve them. We're going to be using the inverse ratios to check our work. So, we have some angles in this diagram, D, E, and F. And like a riddle, we have to figure out which angle is being talked about. So, for part A, the sine of our mystery angle is 12/13. Well, how can we figure that out? My recommendation is set up a trig ratio. If the sine of the angle is supposed to be 12/13, that means that the sine is really just opposite over hypotenuse, right? It's telling us that the opposite side from our angle is 12, and the hypotenuse is 13. So which of our angles is across from 12? Since angle E is the only one that has 12 as its opposite, it's E. For B, the cosine of an angle is 12/13. So we recall that the cosine of any angle is adjacent over hypotenuse, so ka toa. So that means that 12 is the adjacent side to this angle. Be careful because there are two angles that have an adjacent side of 12. How would we know which is which? Well, remember our rules. All these rules that we've done so far have only dealt with acute angles. It turns out that right angles are a bit weird. They're always going to give us some weird decimals or fractions, in the sense that we're going to get ones or zeros or just something that breaks our calculator. Angle F being 12/13 makes more sense because D, as our right angle, has two adjacent legs. We don't want to deal with angles that have two adjacent legs with a cosine. So, by process of elimination, angle F is our mystery angle. And if the tangent of an angle is undefined, we mentioned this a little bit in the last class, but if you take the tangent of a right angle, your calculator freaks out at you. We get an error. So, anytime you want to take the tangent of a right angle, you're going to get undefined. D is the angle being questioned. Cool. Now, before we move over to the back side, I want to talk about another definition here. I want to talk about solving a triangle. Solving a triangle is sort of our end goal for this section. It's what we're building up to. Solving a triangle means to find all sides and angles in a triangle. Just finding all the missing sides and all the missing angles, which we can now do because we have a way of figuring out angles. But there's a catch. For right triangles, You can't just go in with no information. There's a bare minimum of information you will need. You can do this if you have two side lengths. If you have two side lengths, well, you can solve for the third using the Pythagorean theorem, and you can solve for the angles using inverse trig. Alternatively, one side, one acute angle. If we're dealing with a right triangle and you've got another acute angle, you can find the third angle knowing that all triangles add up to 180. Then you can use regular trig, because with regular trig functions, you know the angle and you're finding the side. Let's take a look at exercise 3 and see if we can apply this knowledge. We're going to look at 3a, and then we're also going to do 3d. So, for problem 3a, we have a right triangle, and we're asked to solve this right triangle. The thing is, do we have enough information to solve this? Well, according to our notes, we need to have either two sides or an acute angle and a side. And we definitely have two sides here. So, we just need to find the other information. The other information being side C, angle A, and angle B. In order to find these pieces of information, we need to be creative, and we need to use all the tools we've learned in this unit and beyond. Let's start with side C. There's a process we can use if you know two sides of a right triangle to find the third. Do we remember it? It's a little something called the Pythagorean theorem. A squared plus b squared equals c squared, right? We should just first figure out if our unknown is one of the legs or the hypotenuse. And it's clearly the hypotenuse in this case because it's across from the right angle. So, in other words, to find c squared, we should take both of our legs and square them, adding them together in the process. 2 squared is 4, 3 squared is 9, 4 plus 9 is 13, so 13 equals c squared. We can then square root both sides to find that the square root of 13 equals c. Should we simplify this square root? Well, we should try to, but this one actually can't be simplified any further. Why not? Well, because 13 can't be split up into two perfect squares. Or sorry, into two squares. There are no two numbers that could multiply to make 13 besides 1 and 13. So there's no need to simplify it. We've got the easy part done. Now it's time for the tricky bit, solving for angles A and B. To do this, I recommend starting by picking one of the two angles. I'm going to pick angle A. Using the information you know, you get to decide to set up what kind of trig function you want. Technically, we have all three sides now, so you could use any of the ratios. I just don't particularly want to do any math with the square root of 13. You could, and you'll still get the right answer, but that's a little bit more complicated. I'm going to take a look at the other two bits of information I have. So, ask yourself, how does angle A relate with this side and this side, for instance? Well, it's opposite from the side length of 3, and it's adjacent to the side length of 2, so what trig ratio involves an opposite side and an adjacent side? That'll be tangent. So the tangent of angle A equals 3 over 2. Cool. That doesn't really give us an answer because we're trying to find the angle, not the sides. So we can use our regular trig function to make an inverse trig function and solve for angle A. To do that, remember that the inverse tangent of our ratio, 3/2, will equal our angle, A. This we can plug into our calculator. So, we take the inverse tangent of 3 over 2, and we get that angle A is 56.3 degrees. A is about 56.3 degrees. Nice. Now, we could use a similar process to solve for angle B, but my question is, why make things more complicated than they need to be? We already have two angles on our triangle. We have our 56.3 degree angle, we've got our 90 degree angle, and we know that the sum of all angles in a triangle should be 180. So to solve for B, really all we need to do is ask, what should B be to make 180? Or, if you want to use the shortcut, remember that these two acute angles should add up to make 90. So 90 minus our other angle, 56.3, will equal what angle B is. If you didn't want to use the rounded version of the answer, because again that'd be rounding twice, in your calculator you can do 90 minus, and then there's an answer button above the negative. You can click that answer button and it'll use your previous answer. 90 minus our previous answer is 33.690. So 33.690 rounds up to 39 or 33.7 degrees, since it's asked to round to the nearest tenth. Done. 33.7 degrees. Let's take a look at problem D as well, because D is a little bit different. In problem D, we don't have two sides that are given to us. We have a side and an angle. So we need to think of a best approach to solve this. My recommendation in this case is to recognize that we're only missing one angle in our triangle, right? Angle G. Well, we know that 25 degrees plus G is supposed to equal 90, so we can say that G is whatever 90 minus 25 is. 90 minus 25 is 65 degrees, so G is a 65 degree angle. We got all of our angles done. We're already halfway there. From here, we just need to solve for the missing sides. Now, if we know two sides, we can use the Pythagorean theorem. If we only know one side, we learned that we have to use our trig ratios. And mind you, it's our regular trig ratios. Inverses are used to find angles. The regular ratios are used to find sides. So, how do we do it? Just like before, start with your angle. We have the angle of 25 degrees, and we know the hypotenuse is 13. So we have to involve the hypotenuse somewhere in our ratio. There are two ratios that involve the hypotenuse, the sine and the cosine. The sine of an angle, so the sine of 25, is always going to equal our opposite over hypotenuse. That would be h over 13. But if you wanted to use the adjacent over hypotenuse, we could find the cosine of 25, which is g over 13. And look at that, we've already set up two equations to solve for h and g. We just got to solve them. We multiply the first one by 13, and we get 13 times the sine of 25 will equal h. Same with g. We can multiply both sides by 13 to get that 13 times the cosine of 25 equals g. All we got to do is plug them both in. So, oops, here we go. Let's start with 13 times the sine of 25. 13 sine of 25 equals 5.5. So, h is about 5.5. For the cosine, we have 13 cosine 25, which is 11.8. So g is 11.8. Done. These problems are as quick as you would like them to be. You can take your time. You can solve in some various ways. You could use the Pythagorean theorem. But overall, do what is easiest first, and the problem will go by quickly. Which is useful because I want you to try out problems B and C on your own. Pause the video and give them a shot. Feel free to check your answers, folks. Here they are. Now, the last type of problem that we're going to be seeing today, other than our word problem, involves our final definition of the day, the area of a triangle. Mr. Strager, wait a second. I already know the area of a triangle. You know the area of some triangles. Let me explain. We know that the formula for an area of a triangle is as follows. It is the area of a triangle is 1/2 base times height. Fantastic. Wonderful. You can absolutely use this anytime you like. As long as you know the base, and as long as you know the height, you can use this formula. But we won't always have the base and the height. In fact, most commonly, we're not really given the height of a triangle. What we're really given are the different side lengths, like 13, 15, and like 6. This presents a problem because finding the height is not easy. We learned a case where it's easy to do, which is if you have an equilateral triangle. If you have an equilateral triangle, you can cut it in half and end up with a 30, 60, 90. But that doesn't work for other triangles. So we need a new method to find the area of a non-right, non-equilateral triangle. This is where the formula comes in for the area of a triangle. This is going to be a weird formula, fair warning, but then we're going to explain it. The area of any triangle is the product of 1/2 times 2 side lengths times the included angle of those sides. Mr. Strager, what on earth are you talking about? Well, let's take a look back at our big triangle up here. The area of a triangle equals 1/2. And instead of the base, we can use any letters we want. We just need 2 sides. Let's say I wanted to use sides B and C. Whoops, I'm sorry. I realized I forgot part of the definition. We want to use the sine of the included angle of those sides. The included angle between B and C would be A here. So 1/2 times BC times sine of A would be a formula we could use in this triangle. We really don't need to attribute certain letters to certain angles for this one, though, because it's universal. As long as the angle is in between the two sides, we can use it. So let's take a look at example 4 and see it in practice. Here we have an obtuse triangle, and to find the area, recall that we can use 1/2 times the lengths of two sides, so 19 and 17, times the sine of the included angle. Since 135 degrees is wedged in between those two, we can use it. Just like that, we can go through and actually solve this problem. We can type in 1/2 parentheses 19, parentheses 17, sine of 135. That's the area. That is the area of the triangle in one formula. 114 point, since it says to round to the nearest tenth, 114.2 units squared. Done. Anytime you have the two sides and the included angle, you can use this formula. Want the area of this triangle? Well, we have to do 1/2 times 13 times 15, since those are the two sides, times the sine of 57, since that's the included angle. We go through and do, once again, 1/2. This time I'll just use multiplication symbols. Times 13 times 15 times the sine of 57. That's the area. 81.8 units squared. Quick, right? That problem took maybe 30 seconds. Overall, use this formula to your advantage. It's a much quicker way of solving a lot of problems. Let's take a look at the very last problem of today, exercise 5, which is a word problem. This is actually accurate to my knowledge. The Uniform Federal Accessibility Standards. This is a set of standards set for different accessibilities, such as wheelchairs. They specify that a wheelchair ramp should not have an incline greater than 4.76 degrees. In other words, they don't want it to be a huge angle because then wheelchairs won't be able to get up them. 4.76 degrees is a very shallow angle. We want to build a ramp with a vertical rise of 8 inches. And we want to make sure we're using the minimal horizontal distance taken up by the ramp. We should show a diagram showing the approximate dimensions of our ramp. Here's the thing, folks. If we want to minimize the horizontal distance, why can't we have a ramp that looks like this? A ramp that goes up the 8 inches that we wanted here, and there's x. But because this angle is so steep, this angle here wouldn't make sense for a ramp. If we want to use the minimal horizontal distance, we should stretch out this ramp just enough so that the angle is within our acceptable standards. Our ramp should actually look more like this. In fact, even this might be a little bit too steep, but my drawing isn't perfect. If we want to rise 8 inches, this is how we would set it up. We need the approximate dimensions of our ramp. That means we need to know all the different sides and all the different angles of the ramp. Good news is, we're sort of pros at that already. We did it in exercise 3. Let's solve this triangle. So, in this triangle, we have 2 angles and we have a side. We need to find x, y, and I'll call this angle Z, just because why not? Sorry, no, this would be angle x. My bad. So, what would be the easiest thing to find? Well, since we know two of the angles, we know that angle X is supposed to be the third angle. We know that X and 4.76 should add up to make 90. So 90 minus 4.76 will give us the angle for angle X. 85.24 degrees. Nice. Now we've got to find the two sides. Once again, I recommend starting by picking an angle. Since we already have the 4.76 at the beginning, let's use that. Our known side is 8 inches long, and it's the opposite from the angle. So what ratios involve the opposite? Well, we could do the opposite of 8 over the adjacent of x. That would be tangent. So the tangent of 4.76 equals 8 over x. If we wanted to solve this, we can use our little shortcut we learned a couple class periods ago, which is to switch the entire side of the equation with the entire denominator to get x by itself. X equals 8 divided by the tangent of 4.76. You can do this anytime your variable is in the denominator. Mr. Strager, why didn't we use an inverse? Because we're trying to find a side length. And anytime you're trying to find a side, you just use the regular tangent. So in our calculators, we do 8 divided by the tangent of 4.76 and find a whopping 96-inch long ramp. That is what x is. X should be around 96.1 inches. Cool. To find y, we can set up another ratio. Just figure out which one to use. Since 8 is across from 4.76, it's the opposite, and y is our hypotenuse, so the sine ratio is one that uses the opposite over hypotenuse. Once again, we can use our switching trick to get y by itself. Y equals 8 divided by sine of 4.76. Then we put this in our calculator. 8 divided by the sine of 4.76 is 96.40. Very close in length. But it makes sense. Whoops. But it makes sense. After all, 8 inches compared to 96 is an incredibly shallow ramp. These two lengths would basically be the same thing. So there we have it. Thank you so much, everybody. That will conclude our lesson for today. I hope you have a fantastic rest of your night.